Alright guys, welcome back to another video, and today we will be doing the integration of inverse trig functions. Previous videos we have discussed the differentiation of inverse trig. Now we're going to see their applications to integration. So you may be wondering, how do we actually get the standard trig inverse trig identities from this function? Well, we can use completing the square. Completing the square will allow us to get a square plus another constant which matches the inverse trig identities. So by doing this, you will just get x squared minus 4x times half squared plus 4 minus that plus 13 dx. And this will equal to integral of 1 over x minus 2 squared plus 9 dx. Sorry for bad handwriting, but 9. Anyways, now you can see that you have x minus 2 squared plus 9, and it kind of looks like the tan, right? Tan inverse. But how do we make it such that it's exactly the tan inverse? Well, we have to use a technique called U substitution. U substitution lets a composite function it's like the reverse chain rule. You find this function, and since it has like a power to it or anything on the denominator, you can let u equals that inside function, and you will get the tan inverse identity. So integral of 1 over u squared plus 9 du. The reason why I can already say it's du, because when you differentiate x minus 2, you would get just 1, and then therefore du equals dx, and therefore dx will just match to du. And now we have this substitution, u equals x minus 2. And now, you can see something beautiful going to happen. Now that you see u squared plus 9, you can connect this to the primitives. So what do I mean by a primitive or the antiderivative? You may see this in exam questions where they ask you to find the antiderivative. Well, basically, it's the function that is being differentiated. So if you have x squared and you differentiate it to 2x, the primitive is x squared because that's the function that's being differentiated, for example. So now that we have this, we can recognize that the identity for differentiation is this, tan inverse of u on a differentiation of that will equal to a over u squared plus a squared. So this is the differentiation identity, and as I said from earlier, so the differentiation of this is the primitive, this is what we're trying to find, and this is the result from the differentiation. So now that you can see that we have nearly the matched identity, we just divide by 1 over a. Times by 1 over a, and you will get this. And now you can see that this matches the integral exactly, and we've reached our goal. But we are not done yet. We need to still find what a is. What is a? We have to compare the coefficient, and by simply a squared equals 3 and a equals 3. So now that we've found that, and we have u equals x minus 2, all we need to do is just sub these in to whatever the primitive was. So, simply, we will clear the whiteboard, but I hope you know that a equals 3 and u equals x minus 2. So, just for another repetition for note-taking purposes, you can say 1 over a tan inverse of u on a equals the derivative of this will equal u squared plus a squared, matching the integral we had. Squared plus 9 du. It was matching this integral we had, remember? So now, all we need to do is a equals 3, and whatever u we let in our u substitution for earlier, which is x minus 2, now we just simply sub it in to the primitive. This is the primitive. 1 over 3 tan inverse of x minus 2 on 3 plus c. Don't forget, because this is an indefinite integral and we need plus c. So this is the answer. 1/3 tan inverse x minus 2 over 3 plus c. Let's do another question. Another question that is very commonly seen is this. We're not using tan anymore, but there's a sneaky technique that we can use. This is called u substitution again, where we let u equals x squared. Well, why am I doing this as u equals x squared? You're letting it be based on whatever identity you can find. It is usually in the denominator, and you can cancel out the numerator and find something in ln. But this is not the case, and we can use a standard trig identity to find it. And what I am thinking of is, what do you think? The sine inverse. Anyways, don't forget to differentiate u to remove that dx, du dx equals 2x. And therefore dx equals du on 2x. And by simply doing that and removing the coefficient, you get a half at the front. And then you get 1 over root 1 minus u squared du. Then again, recall a process fully primitive. When we find sine inverse of u on a, the derivative of this will just simply equal to root a squared u squared minus a squared. There we go. And by simply seeing this, a squared minus u squared. If you ever forget which one's the a squared and which one's the u squared, you can simply look back at your substitution. You see that from this, you're trying to match what you differentiated, right? So a will just equal to 1. And therefore, since we found a equals 1, right? And this matches whatever we had, this is simply just sine inverse u. So now we have found the primitive sine inverse u. But don't forget, we had this half at the front. So our last one will be half sine inverse of u. And don't forget that we have u equals x squared. So half sine inverse x squared, don't forget the plus c because it's an indefinite integral. Okay, I hope these two examples will help you on your calculus journey and see if any of these made sense. Finding the primitive and deriving this from first principles is one of the most important steps. Anyways, we are going to cover the applications to integration with volumes and spheres and everything we have next video. So I hope you enjoyed.